Wait, the session. So I just made the recording to begin, and then the live stream on YouTube is also ongoing. So I can easily hand it over to. Okay, so good afternoon once again to everyone. I'm Fejiro, and a privilege to welcome you to the officially uh, program for the energy mentoring session hosted by Lecture Hub and our mentor, Mr. Uchechukwu Imo. So Mr. Uchechukwu will be the mentor for the seismic data acquisition and interpretation. This being our officially first week, will no longer be more of an introductory class, but will be directly into the outline on how each of the mentees can easily acquire seismic data and at the same time be able to interpret data for a reasonable decision-making process in their own respective field or engineering background. So I would love to welcome Mr. Uche Shuku to go ahead with the session for the week. Thank you very much, sir, for your patience and your availability. We can react on the comment section, please. Thank you.
Okay, Fejiro, thank you for your time. Thank you, everyone. Today we are starting. Can I share my screen now?
Yes, I'll make you officially the host, but you have to make me a co-host just in case.
Okay.
Okay, I've made you the host. You can make me a co-host.
Okay. Okay. So good afternoon once again. Today we are officially starting the program, and we are going to be talking about seismic acquisition and interpretation, which is actually the topic given. So first I will share my screen on that. Can you guys see my screen?
Not yet, it's still coming up. Yes, it's up now.
Okay. So what next? I need to make you a co-host, right?
Yes, please.
Okay. Okay, I've done that. So
Okay, I've seen it.
okay, we'll continue. Uh, so let's dive in. Last week we did our introductions, and this week we are starting off. The topic Lecture Hub gave me is seismic data acquisition and interpretation. And last week I told you that our aim, I believe the aim for this program is to try and bridge the gap between the classroom and the industry. And we attempt to achieve that by teaching young professionals in the geoscience field about the seismic data you will always encounter if you are working in the oil and gas industry or in any of the energy transition industries, like carbon capture and storage, geothermal energy, even if you are in the geoengineering section, you will come across seismic data and you'll be using them. So what are the objectives of achieving this aim? I told you I'll be teaching you the fundamentals of the seismic method of exploration. I'll take you on how the seismic data is acquired as acquisition. I'll also talk about processing, and then I'll talk about interpretation. All this will be aimed also to help boost your confidence about the seismic data and attenuate any entry-level fears you have. I told you due to one or two limitations you may encounter in school, when you come into the industry, especially from my experience, you see interns, they don't have any idea about what the seismic data is all about. Even those who are currently doing NYSC and all that. I was once like that, and that is why I will be helping to bridge this gap. The topic is seismic data acquisition and interpretation, but in ideal sense, you can't just go into acquisition and interpretation if you don't understand the fundamentals between the seismic method. Okay, that is why for the schedule, I will start with seismic method, the fundamentals. And then by subsequent classes, we'll talk about acquisition. And then I will bring in processing, which is something a lot of persons, students, and even people in the industry, professionals who are into interpretation, have no idea about processing. And I will try to throw a little light so that you have a wider view and understanding about the data you work with. So for today, I'll take you through the seismic method of geophysical survey. Okay, what this method is all about and all that. And for our outline, I've introduced the method. I will give you the advantages and disadvantages, and basically what you see on the screen will, and other things will be what we'll be talking about today. So when we say seismic method, what do we mean? It's simply a geophysical exploration tool or method where you send in seismic wave. When I say seismic wave, I mean sound waves into the ground or to the subsurface. And the seismic waves are propagated and reflected back to the head surface, okay? So it involves artificially generated seismic waves and the interaction with subsurface materials. And the aim is to create a detailed image of the subsurface or the Earth's interior. Okay, the seismic wave, as you can see from, are you seeing my mouse? Do I need a pointer? Okay.
Yes.
So we can see it now. You can see it
Okay.
now, sir.
Okay, so you can see from the cartoon illustration, the truck. The first truck on your left is a source. The vibrosis truck generates a seismic wave, and the wave will propagate into the subsurface and then go back up to the surface again. So the wave will either reflect according to the dashed lines or refract according to the white continuous lines. Okay, and the aim of this is to acquire information of the subsurface, and it plays a significant role in our understanding of the subsurface rocks, their structure, their stratigraphy, and rock quality and all that. So that would be that. Then what are the advantages and disadvantages of the seismic method? The seismic method of geophysical exploration has the ability to cover a wide area or extent. So for that, it's used in the industry when you want to image a very wide area. So you can imagine, for those of us who may have been in the industry or you work in a company and they tell you the company has an oil block, OML this or OML that. The oil blocks are usually large or wide, okay? And you use the seismic data to image the subsurface over the whole block. So it has a wide area coverage. Okay, it also has a great depth of penetration, and then it can produce detailed image of the structural features present in the subsurface. So no matter the depth of the structural feature, the seismic method has an ability to image the subsurface and identify the structures. Then it can be used to delineate stratigraphic and in some cases the positional features, and can also dictate lateral and depth variations in the subsurface rocks. So while it covers a wide area extent, it also identifies lateral changes within the rock and also vertical changes within the rock as it covers great depth. So on the disadvantageous part of the seismic method, it's quite an expensive method. So seismic surveying is not something you graduate from school and you set up your own company. It's an expensive business to buy the equipment or the acquisition equipment, even the acquisition companies, the vibroseis, the receivers and all that. Everything is expensive. Then the data acquisition is expensive, especially the logistics, and the acquisition process can be intense. So when it's always an intensive project, requires a lot of planning and a lot of cost is involved. So it's not usually cheap, and it's when part of being intense is that it takes a long time. So seismic acquisition can take months or months and months. I know a current project by one of the Nigerian indigenous oil companies that has been on for the past 2 years, acquisition project. And so you can imagine how intense that can be. So it doesn't give you room for errors and all that. Amount of data collected can be so enormous. So imagine acquiring data for a whole 1 year. So imagine the amount of data you would have required in terms of data size, running into terabytes of data, tens and tens or hundreds of terabytes of data. So it can be quite enormous and overwhelming, and the data management is very key. So that's one of it. And data acquisition and processing can be time consuming. For those of us who have been in processing centers, it takes quite a while to process seismic data. And then it requires a sophisticated computer hardware. It's not something, maybe for casual work, you can use some high-end laptops and all that, but the real deal is done with sophisticated supercomputers. When I mean your servers and all that, prod servers and GPU servers. So, and these things are expensive to acquire. So that could be the downsides of it. So the seismic method, when it comes to application, it's a tool that is being applied in various fields. Number one, for exploration purpose, for those of us in the oil and gas industry, what we are doing is exploration seismology, or seismology. And so the seismic data is used for exploration purpose for oil and gas, where you're doing carbon capture and storage, where you're doing reservoir monitoring, geothermal resource monitoring or exploration. For those in the Western world where geothermal energy is a source of energy, they also use the seismic method to image the subsurface and identify these geothermal hotspots and all that. So it's used in exploration. So when you're using seismic data for exploration, the image, the depth of penetration is about 10 kilometers into the subsurface. So you image about 10 kilometers down. That's like 10,000 feet on approximately, plus or minus maybe 2 or 3 kilometers. So that is it for exploration. Also, we use seismic method in engineering surveys, that's engineering seismology. Now, for the exploration seismology, we use the seismic method that actually reflects. So I will explain that as we proceed. Then for the engineering seismology, the seismic method that is also being used is mostly the refraction seismic, and it's always done for shallow subsurface imaging up to about 1 kilometer. So when you're looking for doing mineral exploration, like you're exploring for coal, you can also use seismic method to explore for coal. That's mineral exploration and other solid minerals. You can use them for environmental and engineering studies, and also civil and infrastructural development projects. You also use seismic method for groundwater exploration, that is the engineering seismic method, or this engineering seismology, geohazard assessment, archaeological and cultural heritage studies. So it has a broad spectrum of usage. So while you are studying as a geophysicist or a geoscientist, don't just think that the seismic method or that you've been taught in school ends with the oil and gas industry, because that's what our school systems tend to teach us or tell us. But the application is beyond just the oil and gas industry and all that. So, and the last is the earthquake seismology, where the seismic is used for earthquake studies and seeing subsurface structures above 100 kilometers down, where you study the image of the earth interior, or the earth interior structure from the core to the mantles to the crust. Like I remember on Monday, I gave you a link where you can just read about the earthquakes or seismology. I'm sure some of you must have read that, where you saw the application of a seismic wave through earthquakes to study this earth subsurface. So the seismic method of exploration stems from the earthquake seismology. Earthquake seismology, the seismic wave is naturally generated by earthquakes. So scientists over the years came to find out that you can also apply it in the first two methods, that is exploration seismology and engineering seismology, to image the subsurface. And this, in the first two methods, what you do is to artificially generate the seismic wave rather than naturally wait for earthquakes to generate seismic waves. So that is it for application. If you have any questions so far, you can raise your hand and the moderator will call my attention to that. So, having identified that the seismic method has to do with the generation of seismic waves, and the waves. If you're not speaking, please mute your microphone, please.
I never remember.
Okay, ask to mute. Daniel, please mute. Thank you. So, as we have identified, the seismic method has to do with generation of seismic waves artificially. And so we have to understand what are seismic waves and how do they operate. Okay, so the waves that propagate through the Earth's subsurface are known as the seismic waves. And these waves they are just periodic vibrations, okay, that sends energy through the subsurface rocks. And as they pass through these rocks, they capture information about the subsurface rock. So in other words, I consider seismic waves as information carriers or informants of the subsurface. So they give you information about the subsurface. And there are two types of seismic waves. One is the body wave and one is the surface wave. So the body waves are just as shown on picture on the left. The body waves, when they are generated from the source, the red dots there, they spiral away from the center, from the point of generation. And you can see with increasing depth and increasing distance away from the source, the seismic wave keep transmitting or propagating away from the source, as shown on this diagram. So they propagate away radially from the source in all directions. Okay? That is it for the body waves. And also the second type of seismic wave are known as the surface waves. And the surface waves are the ones that they do not propagate into the Earth's subsurface per se. They limit themselves to the Earth's surface, as shown in the second diagram. So when this wave is generated, they keep increasing their distance of travel away from the source. but limiting themselves to the surface and the near surface. You can see this is moving from 0 to maximum of about 80 or 90 meters into the subsurface, and they propagate away from the source in the left and the right direction, in all directions generally, as shown in this diagram. But for the body waves, they keep propagating even at great depths, up to, as shown in this cartoon, great depths above 200 meters and all that. So, having brought this to attention, the seismic method that we are using in the oil and gas industry, which is the reflection seismic method, focuses on the body waves and not the surface waves. So any surface wave that is recorded by the receivers will be termed noise in the seismic data. There will be a noise, and that will have to be eliminated. So our interest will be on the body waves. Okay, so for the body waves, there are two types of body waves. There are the P waves and the S waves. Okay, the P wave, as we see on the cartoon also, at the center we have an undisturbed body of rock. If you generate a seismic wave from the left part of this undisturbed rock, if it's the P wave, if it's moving, it will move longitudinally along the direction of propagation of the seismic wave. So it's compressional in nature. It shakes the medium that is propagating through without actually destroying the medium. Okay, and moves in the same direction of propagation. Okay, they are actually the fastest. If you read the link I gave to you, you understand, or you would have had an insight about this. The P waves are the fastest of all the waves, and they are usually the first to arrive at the receiver, the receivers on the surface, and they can move through solids and liquid. That is very important to note. The P waves, they can propagate through the subsurface and transmit through solids and through what? Liquids. When I mean liquids, fluids rather, through solids and fluid, liquid and gas. That should be that, correct. Then for the S waves, they are shear waves. They are not compressional. So they move perpendicular to the direction of propagation of the wave. Okay. They are the second waves to arrive your receiving stations. So after the P waves, you have the S waves arriving, and they can only move through what? Solids. They don't move through fluids. So we'll get to find out why. So also for us in exploration seismology or exploration seismic, our interest tends to be on the P waves. Most times when you're interpreting your seismic data, you're interpreting those that are acquired using the conventional seismic data. So the focus is usually on the P waves, which are the fastest and the ones that come back to the receivers fast. The S waves are slower. Sometimes they are in use. By the time we start talking about precision, we'll see situations where S waves come into play. But most of the time, it's the P waves. So most exploration surveys uses the P waves as they are the primary source of information. I think I've noted that. So having understood that, when you talk about seismic wave propagation, when the wave are propagating through the subsurface rocks, they travel in all directions, okay? And then the direction that it travels on, which is known as the ray path, is always illustrated as straight lines. But they are moving in all directions in actual sense, and they are spiraling away from the source. But for illustration purposes, you see most textbooks and all that, they will just use a straight line, like the one we are having on our cartoon here, to show the direction of movement of the seismic wave, okay? So that straight line illustration is known as the seismic ray path. Also, as the seismic wave spirals away, it tends to have a circular motion of movement. That circular motion of movement as shown on this blue line, or this blue line that is joining all the ray paths together. That is known as the seismic wave front. For instance, you have a bucket of water or basin of water. When you drop a ball or an object in the middle of the basin, what happens is that waves are generated. That is your ripples. on the surface of the water, and these ripples are operate in circular form. So that the way you see it on the surface of the water is the same way it's moving down within the water body, and the same way it's moving down to the subsurface. Okay, so the wave fronts are usually perpendicular to the ray paths, as shown here. Okay, so subsequently, when you see a straight line illustrating the seismic wave direction or propagation, just know that that straight line is illustrating a ray path. The wave is actually propagating in all directions, but the ray path is used for easy illustrations in textbooks and in learning materials. So what are the characteristics of these waves, the seismic wave? I told you to read up, and when you come across seismic data, you'll be dealing with the characteristics of the seismic wave that was used to acquire the seismic data. Every wave have these natural characteristics, be it the surface waves, the body waves, the P waves or the S waves or the body waves. All of them have these natural characteristics. What do they mean? One, I'll be talking about frequency. Frequency simply means the number of oscillations or waves that pass through a point at a given time. Okay, so and it's usually measured in hertz. So if you're dealing with seismic data, especially for us in processing, we'll be very much, even for an interpreter, you'll be very much interested in the frequency of the seismic wave that was used to acquire the seismic data. So in acquisition, we have a broad band of seismic waves, seismic frequencies that are used. And there's what we call the low frequency waves, the dominant frequency waves, and the high frequency waves. So frequency in essence simply means 1/T in terms of formula. T means period or time. Then on the cartoon on the right, you can see an illustration of what frequency means. So if you look at the cartoon, you can see the image showing the upper image showing the frequency of a wave. You can see the lower frequency means that the seismic wave makes lesser oscillation within a period of time. So if you can make a count from, let me change to a pen. Okay. So if you can count from here, or let's say we count from here, the wave starts making it's my color. Let me see about that. So if the wave starts here, and you have to count, by the time the wave moves and come back to this point again, it has made one oscillation. So that is one cycle or one complete oscillation. From here to here is another complete oscillation, and here to here is another complete oscillation. You can actually start counting from any point on the wave that you like. You can also start counting from here. From here, the wave goes round and come back to this end. It has made another complete oscillation, and then to this point, another one, and this, another one, and then lastly this one. So if you are to tell me, what do you think is the number of oscillations that this wave has made over this time period? Anybody? 4. Okay, so the frequency of this seismic wave is 4 hertz. Okay, 4 hertz. Hertz is Hz. That's the sign or the units. Okay. For the second one, I want you to count. I won't make any input. So count and tell me how many hertz you see.
6.
So 6. So any other person? I don't want only one input. Any other person? How many did you count?
6.
I need another response.
I
Counted
counted
6.
6.
6 too. So we'll count from here. 1, 2, 3, 4, 5. Okay. So it's 1, 2, 3, 4, 5, and 6. So here we have what? 6 heads. So it simply means that the wave above made an 4 oscillations within the period that we are looking at from the beginning to the end. This period, this could be in 1 second time. So from here, the point A to point B, the seismic wave may have just, it could be just 1 second, okay? It could be, depending on what the duration of time given, the time is. So within approximately, let's say 1 second, this first wave has made only 4 oscillations, which is 4 hertz of that. So the frequency is 4 hertz. The second one made the same, cover the same distance, or maybe the same within the same time frame. It made 6 oscillations, that is 6 hertz. So the frequency of the second one is higher than the frequency of the first one. So frequency is very important as a property of the wave, because it shows how much oscillations the seismic wave is making, or how intense the frequency of the seismic wave is. Because we are trying to image the subsurface, the frequency helps to control the resolution of the seismic data, or it's the frequency that actually determines the resolution of your data. So it's a very important character or property of the seismic wave, and we'll learn more about it. Now, the frequency of the seismic wave also determines its wavelength. Okay, when we talk about wavelength, this is from this point to this point, the length of one peak to one peak, and the next peak to the next trough. Assuming this is positive, or which it is, and this is negative. So this is your peak when the seismic wave is oscillating towards the positive side. That's the peak. And when it's oscillating, turning toward on the negative side, that's your trough. So this is your peak for P and your trough for T. So that is it. So for the low frequency waves, their wavelengths are usually longer. And for your high frequency waves, the wavelengths are usually shorter. So the next thing we will look at is your amplitude. What does amplitude mean? Which is also a very important property or characteristics of a wave. So the amplitude is the highest deviation of the wave from its center, or the zero position. So as we can see on the next cartoon, which shows 2 sets of waves. Now, because seismic waves are like sound waves, so this illustration is using this angry bird. So the pitch of the sound of the bird, if the pitch of the sound that you hear from a sound generated from maybe a radio or a sound speaker is high, it means the amplitude of that wave is high. The amplitude can also be low. The amplitude does not control the frequency. That the amplitude is high or low does not have any effect. The frequency can actually be high or low frequency, and amplitude can also be low or high. They are not directly related. That is the point I'm making. So in other words, amplitude is just the intensity of the seismic wave. So the first one is showing you on the positive side, you see the wave propagating. The wave will have the same frequency with the one below. Okay, but you can see that the amplitude of this wave, if you can read it off on this graph, let's assume this point is 1, and here is 1, 2. So what can you say the amplitude is here? If you are to scale this graph roughly, any idea, anybody? If you're to scale this roughly, okay, I'm not getting any response. Are we together? Do you still hear me?
Yeah, we too.
So if you are to scale this one roughly, what would be the amplitude there? This is 1. The highest point on the positive side is 1. The highest point on the negative side is also 1. So what would be the amplitude of this first wave?
0.25.
Okay, that's nice. 0.25, good. It can be record, and the unit of measuring amplitude is usually decibels. Okay, so if you're working on a processing software, you have your frequency spectrum showing your amplitude and frequency. You will be looking at the amplitude side, and the unit is usually either decibel, or they'll tell you that it's normalized. They can normalize it depending on if you have more than one waves that you're comparing. Okay, the next one, what do you think will be the second one? The second wave, what would you think is the amplitude? Any response?
Like 0.75.
Okay, like 0.75 or maybe 0.8 or whatever, 75. So you can see the amplitudes are different, but their frequencies, are they the same? Someone else will tell me, are their frequency the same? I need response from someone else. Are the frequency of the two waves, I mean on this graph, so their frequencies are the same, but their amplitudes are not the same. Good. So the amplitudes are not the same, but their frequencies are the same. So frequency does not affect amplitude. Neither does amplitude affect frequency. So you can have high frequency, low amplitude, or high frequency, high amplitude, or low frequency, low amplitude, whatever way it wants to come. So amplitude is very important because when you start looking at your seismic data, online, and what you're seeing there that are looking like lines are just they are amplitude responses. Okay, the amplitude responses that are coming from the subsurface rocks. So sometimes you see a place, it's looking very dark. Another part of the seismic data is looking less darker. So it's the amplitude response of the rocks in those places. That is what you're looking at. So it's those amplitude response that you are going to be identifying as a geoscientist. When you're trying to interpret the seismic data, your interpretation of the data is dependent on the amplitude, because you're not seeing, as your normal natural eyes cannot see frequency. It's the equipments that measure the frequency. As a human being, you cannot see frequency with your eyes. So, but you can see amplitude. So if those amplitude is transmitted to you as maybe dark lines on your seismic data or faint lines on your seismic data. So that's why amplitude is very, very important. So I'll proceed to the next slide that talks about a period. Okay, period is the time taken for waves to make one oscillation. I think I threw light on that in frequency discussion. And period is the same thing as 1 over frequency, just like frequency is the same thing as 1 over period. Okay, so period is the time it takes for a wave to make one complete oscillation, and it's measured in milliseconds, because it's a time property of the seismic wave. Is measured in what? Milliseconds. How many milliseconds make 1 second? Any idea? Uh, 1,000. Good. 1,000 milliseconds will make 1 second. So where's my mouse? So 1,000 milliseconds will give you 1 second. So if you're looking at a typical seismic data, especially the raw seismic data, you'll be seeing things like 1,000, 2,000, 3,000, 4,000. They are the same thing as second. Okay, yeah. Make 1 second rather. 1 second. Forgive my right topo. Okay. So the next thing we'll look at is wavelength. I try to explain wavelength. So when you have a peak, and maybe the seismic wave. You have a peak here and another peak here. The distance between the top of these two peaks is your wavelength, and the distance between the also the two consecutive troughs is also your wavelength. So the wavelength is controlled by the frequency. If the frequency is high, the wavelength will be short. If the frequency is low, the wavelength will be higher. Okay, and the wavelength is directly proportional to velocity of the seismic wave. And then last thing is that wavelengths are measured in feet or in meters. Okay, they are usually measured in feet or in meters. Okay. Also, on the characteristics of the seismic wave, the next thing we look at is the velocity of the waves. Velocity of the seismic waves. What is velocity? Velocity is just the speed at which the seismic wave is traveling through the subsurface. But for us in seismology or geophysics per se, we don't use the term speed. I purposely left it as speed in this presentation because speed is easily relatable amongst us or amongst an average person. When you say speed, what is the speed that you moved from, your vehicle used to move from one place to the other? If you're driving, you look at your speedometer, it says you're moving at 10 kilometers per hour and all that. But for a seismic wave, we don't usually mention speed. We use the term velocity. So for our brothers in geophysics, what's the difference between velocity and speed?
Speed is a scalar quantity, while velocity is a vector quantity.
Okay, that is just it. So for that, thank you for that. Speed is a scalar, velocity is vector. And why is it vector? Because it has direction, right? Am I right on that?
Yeah.
Yes.
Yeah,
Yes,
vector
sir.
quantities have direction. Speed does not have direction per se. So for the seismic wave, remember we said when it's propagating in all directions, horizontally and even vertically downwards into the subsurface, and spreading out horizontally in all directions in the subsurface. So, and you remember the ray path diagram that we showed, the ray paths are moving in different directions. That is why we are using the term velocity. So the seismic wave is propagating in different directions. So it's a vector quantity. Okay. The seismic, considering the wave travels a distance of one wavelength in one period, the velocity will simply means wavelength over period. Okay, if you look at it, remember the formulas that we discussed earlier. So velocity, in other words, also means frequency times what? Your wavelength. So what is important about velocity? The importance of velocity is that for us to actually use the seismic method to image the subsurface, the velocity at which these waves are propagating through different rocks is very important to us. It's what we are very interested in. It's what we want to measure. Okay, is what we actually want to measure. Now, remember there are two types of waves in the body waves that we use in exploration seismology. So assuming your wave is traveling to a homogeneous medium or a homogeneous rock unit, let's say a clean sandstone with uniform grain size distribution. Okay, distribution in all directions. That is known as, in geology, for our brothers and our friends here who are geologists, that's called a homogeneous, will be described as a homogeneous sandstone unit, right? So that homogeneous sandstone unit, when the seismic wave is traveling through it, the wave velocity will tend to be represented by these formulas, be it the P wave or the S wave. Okay, so for a homogeneous seismic, rock unit, in geophysics, you consider it as an isotropic medium because the velocity of the wave will be uniform in all directions. Why? The rock unit is homogeneous. So does anybody not understand what I mean by homogeneous or isotropic? I would like to, if you are confused there, let me know. Okay, so no response. So for a homogeneous and isotropic unit, medium or rock unit in the subsurface, the P and S waves will travel in all directions uniformly. Their velocity will be the same as they move. I mean, the P wave velocity will be uniform in all directions, and the S in all directions. And for our subsurface rocks, the table is showing us different rock units or different rock types and their P wave and S wave velocities. And wave velocity is measured in meters per second. That's m/second, meters per second. So you have different rock units expressing different velocity properties as the seismic wave propagates through them. So if you look at the table, this velocity with which a seismic wave, let's pay attention to, let's say, the P waves. The velocity with which it will pass through a dry sand will be different, will range from 400 to 1,200 meters per second. And also within the same dry sand, you know, the S waves are slower. So you see that the S wave velocity will be lower, from 100 to about 500 meters per second. But if you look on the S wave side, the velocity of the wave through air, water, and oil, that is your fluids, liquid and gases, the velocities are 0. Why? Why are the velocities nil? So because, as mentioned earlier, the S waves do not travel through fluids. They only travel through solids. So I want to iterate that. The S waves travel through solids and not through fluids. And so the velocity of the waves on fluids are nil. But through solids, you can see them and you can compare. Let's say velocity of the travel of a seismic wave through, let's say, a limestone unit. This one, you can see for the P wave, it's between 3,500 to 6,000 meters per second. For the S waves, it's between 2,000 and 3,300 meters per second. So if you generate a wave through a rock unit that is made up of a limestone, the P waves will move at a very high velocity that we given within this range, and the S wave will travel slower within that rock. So that is what velocity does. And this is very important to us in seismic method. Okay, it is very important to know, because what you're trying to get is the velocity model of the subsurface. Now, each of these rocks, these are their own individual velocity properties, and these velocity properties play a vital role in seismic acquisition and processing and interpretation. So what makes these velocities differ? So as said earlier, if the rock unit is homogeneous or isotropic, it means that the density of the rock will be uniform in all directions, the shear moduli will be the same, and the bulk density will be the same. But we all know that in the subsurface, there is nothing like a homogeneous medium. When sediments are deposited in your basin, there are variations in depositional settings, the depositional environment. You get to the outcrops, which I know most of you have visited outcrops during your school studies, school field trips and all that. And your lecturer tells you to map a particular outcrop, and you're looking at a sandstone unit, for instance, and you're mapping it from left to right or over a distance. You find out that there will be variations within the same rock units. Sometimes the color will change, sometimes the grain size will change, and all that, right? So what does that tell you? It tells you that within the subsurface that the rocks are not homogeneous. The rocks are heterogeneous. So because rocks are heterogeneous, the velocity of travel of the seismic waves will also vary within the rocks. So this heterogeneity leads to density changes. It leads to shear moduli and bulk density changes. And those heterogeneity in geophysics is termed as anisotropy. You can jot that anisotropy, A-N-I-S-O-T-R-O-P-I-C. So is an anisotropic medium is what you encounter in the subsurface. And that anisotropic medium is what we'll be looking at. So the next thing we'll talk about in terms of the rock property, velocity changes due to changes in rock property. One of the property of the rock that affects wave velocity is the bulk modulus or the bulk moduli, which simply means the compressibility of a rock. So if you have a unit of rock that is showing this initial volume, when that rock is compressed by pressure in all directions, the volume of that rock will reduce and it will give us this final smaller volume. Okay, so what makes a rock become compressible is, you know, when we are dealing with mostly sedimentary rocks within sedimentary basins. And so when sediments are deposited, initially what happens? They become compacted. That compaction is the compressibility of is the compression we are talking about here. And the bulk moduli determines is what determines the amount of compressibility that the rock will undergo. And that compressibility, in other words, relates also to what will now become the density of that rock. Then the next thing we'll look at is the shear moduli, okay, which describes how difficult it is to deform a unit of rock. So you have a unit of rock that is initially square in shape, and you're applying a force to it from one direction to it, or maybe in another direction. How easy is it for that rock to deform or to change shape when that force is being applied? Remember, for the bulk moduli, force is being applied in all directions to the rock. So pressure is applied in all directions, or force is applied in all directions in bulk moduli. But for shear moduli, the rock is being pressured from one direction, okay? And so the shear force is pushing it in what direction? How well does the rock bend? So you know that most rocks will bend, but does shear moduli occur in fluids? No, it doesn't. You can't push fluids or in any direction and they will bend for you. So that is the reason why your S waves, as we see in the formal the formal equation we showed here, your S wave, the formula shows it has what? It has shear moduli and density, but it doesn't have the bulk moduli in the equation. But for the P waves, it has the bulk moduli and the shear moduli and density all in the same equation. And shear moduli within fluids are 0. So if you bring 0 into this equation here, whatever the value of density is, if you put 0 into this equation above here, everything will ground down to 0. And that is why the velocity, the S waves, when they get to fluids, because fluids do not have shear moduli, what happens? They do not transmit. I don't know if that makes sense to you. So gases and liquids, in other words, fluids, do not support shear forces. And so that is why your S waves do not travel through fluids. So having said that, the next property of the rock that has direct effects on the velocity of the seismic wave is the density. So remember your bulk moduli that says the compressibility of the rock. So in nature, or in your sedimentary basin, when you have a sedimentary rock being deposited, what happens? Over a period of time, another set of sedimentary rocks are deposited over it. We say this rock is overlain and the other one overlain by this one, and all that, and all that. So let's see some messages. Okay. So some more sediments are being deposited over a period of time, over and over and over. Let me see if I can illustrate that by drawing pen. Okay. So we know that sediments are deposited layer by layer in the subsurface and all that. So we have these different layers of sedimentary rock. So let's say this is rock A, B, and C and D. This will be deposited over geologic time. What happens? By the time the weights of rock B and C and D mounts on rock A, the rock A becomes compacted, okay? It becomes compressed, okay? And when that occurs, what happens? Their volume tends to increase. That's why we talked about the bulk moduli. The volume of the rock will reduce because of compaction due to overburden pressure, overburden weight on the rock. So when that happens, what happens? The density of the rock also tend to increase. Okay, so density typically expresses the gram per cubic centimeter or kilogram per cubic meter of a particular rock unit. And it's very important because as we go through the subsurface, the densities of rocks differs. Also, the factors that actually control density, apart from compaction and lithification, are mineralogy and structure. So your rocks, depending on the mineral that make up the rock, if it's sandstone, you know the sandstone is made up of silica minerals, the quartz grains, and other smaller other minerals like that could be present, mica, feldspar, and all that. The density of these minerals differ. If your rock unit contains some heavy minerals, or maybe your precious metal deposits like gold deposit, the density of that rock will also tend to increase. Now, the porosity of the rock also affects the density of a rock. If the rock is highly porous or more porous, the density tends to reduce. But when it has less porosity, the density may tend to increase. Why? Because the porosity, the grain sizes are more in contact with each other, and the rock volumes tend to be smaller. So the pore fluids and saturation levels also affect density, and then the lithification and segmentation. If you go to the field, you see some rocks that are very hard, that has been cemented by some cementing materials like iron minerals, making them to turn to iron stones and all that. So these are the factors that will affect your density of your rock. And though in essence, the rock becomes more dense. And so when the rock becomes more dense, it tends to allow the propagation of waves through it more easily. And when it's less dense, it tends to prevent the propagation of waves or resist the propagation of waves. So the deeper you go into the subsurface, in terms of depth, the density of the rocks are expected to increase due to compaction, lithification, cementation, and all that, and age. So I believe we understood that. We understood that part. So on the table here, you can see different sedimentary rock units, from claystone or clays to silt to sandstones and shale and all that. You can see there are different density distributions. Okay, the carbonate rocks, limestone, dolomite, gypsum, they tend to have higher densities. Even they tend to have higher densities from 2, ranging from 2 or upwards. While the siliciclastic rocks like sandstones, shales, they tend to have a bit lower density than the carbonate rocks. So in other words, the different rock types in the subsurface have different densities. So as Pashi changes are occurring within the subsurface, the different rock mineralogies are also changing, their porosities are changing, their densities will also be changing, whether in space and in time. So vertically, horizontally, rock units property will be changing. Okay, I hope that makes sense to us. Is there any question? Any question, especially from our geophysics friends? I believe the geology students understood what I explained very well. Okay.
Yes, sir. I have a question, sir.
Okay, go ahead.
Okay, not a question per se. Can you please retake the relationship between density and porosity?
Oh, okay. Thank you. Now, when a rock unit is deposited in time, okay, and then at the point of deposition, okay, the rock will have a porous property, porosity property, in the sense that at that point, let's say sandstone unit, let's use sandstones for illustration. Let me see if I can draw. Let's say this is this box now. You have some rock unit deposited. These are the sand grains. Okay, I'll share
Yes,
this
sir.
into. These are the grains of the sand, and which are in turn the mineralogy within the sand unit. So at the point of deposition, this is the space between these rock units, okay? When this happens, there are more spaces. You can see the sand grains are barely touching themselves. So in other
Yes.
words, the porosity is high. Now, over
Yes.
time, let's say that sand unit is in location A here, okay? So
Yes, sir.
over time, unit B, C, and D gets deposited on top of this sand. So you have other units coming on top of it. What happens is that the sand grains will become closely packed to each other. They become tighter. So the grains are coming closer to each other due to what? Compaction. They are becoming more compact. So remember, I'm illustrating with a supposed cube of rock or volume of rock. So by the time the rock becomes more compacted, because of bulk moduli, the volume may tend to reduce. Okay, it will not be as big as the first one. But what happens is that the grains are coming closer to each other. When this happens, the pore spaces are now smaller than before.
Yes.
The volume of the rock will reduce because in terms of because of compression and compaction of weight on it. So your density will increase, the velocity will reduce. Do you get that point?
Yes, sir.
Now,
Thank you,
if you
sir.
now have minerals, some minerals like ironstone or silica minerals that are transported by in solution, if they precipitate within this rock, they increase the rock, they will litify the rock or cement the rock in place. That's why when you get to the field, you get some rock and you call them stone. They are strong now. They are not fragile. You can't break them with your fingers. They are not friable anymore. Why? They have been litified or cemented by cementing materials, which could be ironstone minerals or iron minerals to turn them to ironstone, or even clay bonding and all that. So that is the relationship between your density and your porosity. So when porosity is reducing, density is increasing, porosity will always tend to reduce and all that. And so that is it. So another thing is, depending on what these minerals are, if these minerals, if you look at them in your petrography, if you look at them under the microscope, if they are made up of heavy minerals, the density of the rock will be higher than when the minerals are made up of lighter minerals, okay? If the grains are made up of things like feldspar, mica, and all that, the density will be smaller. But if the grains are made up of higher end minerals, okay, the density will also more resistant and high dense minerals, the minerals will be, or rather the density of the rock will also increase. That's the relationship between that. So in the subsurface, the rock distribution the rocks that are deposited in space and time have different densities, okay, due to their mineral composition and compaction level and all that, and porosity and all that. So having understood this, I believe I've made it clear the path for us to now dive in deeper into the seismic applications. So finally, on the rock mineral properties, rock properties and the rock velocities, the seismic velocity, which is the rate at which the seismic wave travels that we know, it varies vertically, laterally, and horizontally, and that is known as anisotropy in seismic method, in seismic. Anisotropy, that is, you'll be hearing that a lot if you end up in an environment where processing is done, especially processing in depth. Then heterogeneity, we know that rocks are heterogeneous, so the properties of the rock, be it density or whatever, will always change in all directions, including the properties of the wave that we've seen. So velocity will be the same only in a constant medium, and velocity tends to increase with depth on the subsurface. So what are the factors that can affect seismic wave velocity? The rock type, I've mentioned that. Depth also has a way to affect the velocity of a rock. As the depth increases, the velocity of the rock is expected to also increase, because the deeper you go, the rocks are expected to be more denser. So the denser the rocks are, the more they should allow the transmission of seismic wave through them. Okay, so their velocity of seismic wave tend to increase with increasing depth. So what that means is that you have a graph like this, and this is depth. Okay, this is depth D. Okay, and this is velocity V, increasing from 0 and away. From the surface here, this is like 1 kilometer, 2 kilometer down. Your velocity will be behaving like this. So as you're increasing down, velocity will be increasing with increasing depth. So that's what this second statement means. For the first statement, rock type affects your velocity. So different rocks have different velocities, as shown in the first page. You can see different rocks having different velocity readings and all that. So the next is temperature. Temperature also has a way to affect your velocity because temperature can affect the elastic property of materials. So potentially decreasing your velocity within the rocks. Okay, so this is not a very serious property we'll be looking at, or serious factor we'll be considering. The next thing is fluid content. The presence of fluid like water or gas or even oil can significantly alter the wave velocity of your seismic wave. So if your seismic wave is traveling through the rock unit and you know that velocity is supposed to be increasing with increasing depth. So let's say you have different formations that the seismic wave is traveling through. So if this particular formation here is a unit of sand that is filled with gas, remember velocity is expected to increase with depth. As the seismic wave gets here, the velocity will tend to drop a little and then continue increasing. So you have something like, let me use another color. So you on your velocity profile, you have something like this. On getting to this unit, instead of continuously increasing, the velocity will tend to reduce slightly and then it continue to increase. So velocity is affected by fluid content, especially the presence of gas and water and all that. They have a way of affecting the velocity of your seismic wave. And these are some of the reasons why you encounter, when you're doing interpretation, you'll be seeing some things like your bright spots, your dim spots, and all that. So because your bright spots, you know, as a DHI will help you see where will sometimes be an indicator of the presence of hydrocarbon. Hydrocarbon is a fluid. So their presence will affect the fluid, the wave velocity, and sometimes, and also amplitude and all that. We'll get to that as we progress. So, having laid all this foundation, I will talk about refraction seismic survey briefly, just briefly, because we are in the oil and gas industry. We are more interested on the reflection seismic survey. So for the refraction, it has to do with your seismic survey, where you send your seismic wave into the subsurface. So these are different rock units. This is rock unit 1, and this is rock unit 2, and rock unit 3. So from our previous explanations and learnings, rock units, these different rock units have different densities, okay? And unit 1, unit 2, unit 3 have different densities, and they have different velocity properties, as shown in our previous tables. So let's assume this unit is a unit of sandstone, okay? And this one is another unit of rock, or maybe shell, whatever. Okay, their properties are varying, their velocities vary. So when seismic wave is generated, the wave propagates. I've talked about wavefront. So you can see the spiraling wavefront as it's spiraling away from the source. The source is this hammer that this guy is holding here. So when he hits the ground, the seismic wave spirals away from the source and then moves. When I mean seismic wave here, we mean the primary waves. Now, on getting to the boundary between rock 1 and rock 2, okay, because their properties in terms of velocity and density are different, okay, at this boundary, what happens? The seismic wave will transmit along this boundary. You see it transmitting this red dash arrow. It will move along this boundary of between the, in geology, the boundary is your bedding plane. The bedding plane you see in your outcrops. That is the boundary I'm talking about here. So the bedding plane is where the seismic wave will travel and then travel back upward into the surface where your receivers will pick them up. So this seismic wave that behave this manner, so are known as your refracted seismic wave. So this method is known as a refraction seismic method. So it's used for shallow subsurface survey, like the engineering seismology, where you have up to maximum of about 1 kilometer of survey in the subsurface. So it's used to predict the depth to the bedrock. Now, before I proceed to the next slide, this method will only work or function properly if the velocity of the seismic wave in the first rock unit here, that is velocity 1, is lower than velocity 2. So immediately the seismic wave gets to this boundary, it will refract. And the velocity in layer 2 must be lower, smaller than the velocity in layer 3. The wave will also refract. If for any reason velocity in 2 is higher than velocity in 1 is higher than velocity in 2, refraction seismic survey will fail. It will not work. So the survey results will look something like this. It's used to identify your weathered layer, or what we call the low velocity layer. I will explain that when we start taking you through processing. And then it gives you the method or this refraction seismic method. They are used to predict the depth of bedrock, rock instability, layer thickness, fault zone identification, and all that in the shallow part of the subsurface, very shallow part of the subsurface. So you can see that please mute your mic if you're not speaking. Who is that? Please mute. Fejiro, please help me mute whoever it is. So
Yes, it's done.
okay. So when you have an image like this is a typical result of a refraction seismic survey. You can see that the depth of penetration is from 0 to about, this is in feet, 360 feet, just very shallow within the subsurface. So it requires tractile velocity increase with depth. If there's a velocity reversal, I've explained that in the sense that the layer above has a higher velocity than the layer below. Refraction seismic method will fail. It's very straightforward and easy to apply. You can see it's one man squad that is at the field acquiring it, and it's not as complex as the refraction seismic. So it's used majorly in engineering survey to survey the subsurface for engineering and structural purposes. Okay. And then for us in the oil and gas industry, this method will become handy. I will explain that when we get to that. Let me not boggle you with so much information now. When we get to processing and statics correction, I will come back to this refraction and explain again. So the main interest for today and the main interest for our HOPE mentoring program will be on the reflection seismic survey. Reflection. So for this one, what happens is that this man, he hits the ground and generates seismic waves. What happens is that the seismic wave travels at an angle and hits the boundary between layer 1 and layer 2. Because the rock are having different property, remember, this layer now is a different type of rock. Let's say sandstone. Okay? Sandstone, this one is shale. And maybe this one is limestone, whatever. I'm just assuming. So their velocity properties will differ. Also, the density of the rock will also differ. The density of these different rocks will also differ. So when the seismic wave moves through this in particular rock type, on getting to this boundary, it will reflect. Okay, by reflection. So this one obeys the law of obeys the Snell's law, where you have the angle of incidence is equal to the angle of reflection. If you remember your Snell's law in secondary school, let's say this is the center. So the angle of incidence will also be equal to the angle of reflection. So that is the Snell's law. So the reflection seismic method obeys the Snell's law. Then the wave will reflect. And when it reflects, some of the waves will continue to be transmitted down. So because you can see the wavefront continues downwards. So while reflection occurs at this boundary, transmission will the wave will continue to propagate down or being transmitted down. On getting to the second boundary, there will also be another reflection at this point and at different points, okay? And then another reflection will happen and so on. The wave will continue. When it gets to this other boundary, there will also be another reflection. So it keeps happening that way. And you can see the receivers are increasing in distance from the source. So this is where you generated the seismic wave. And these are called the receivers. We explained that in our acquisition class. The receivers will be placed with increasing distance away from the source of the seismic wave. And this increasing distance is known as offset. So in seismic, please mind my writing. I'm trying to use my mouse pad to make it right. So the seismic, in the seismic method, nobody talks about distance. So when you get to the industry, you're working and you'll be hearing things like offset. Don't allow anybody to use grammar and intimidate you. It simply means what? Distance. So the distance, this is receiver 1, this is the last receiver N. So the distance between these two, the receivers, from here to the last one, that is your offset. You can have that's your maximum offset. Your minimum offset is the distance between receiver 1 and probably your receiver 2. Yes, that's your minimum offset. And then your medium offset will be somewhere here, and then your maximum offset will be here. So as the receivers are far away from the source, the seismic wave will tend to keep going, keep generating or keep traveling to meet these receivers. So the wave, for instance, this receiver here, the wave that it will receive is the wave when this wave front is somewhere in the middle here. That is where it will reflect and come to it. So because remember it's Snell's law, this angle of propagation of angle of propagation incident angle will also be equal to the angle of reflection. So that is it for reflection seismic method. So for your typical reflection seismic results, you'll be having something like what I'm showing you on the screen. You can see this is a typical seismic data showing you your different rock layers and deformations within the rock. So if you look closely, what you're seeing is that some parts are bright, some parts are dim. Like here, some parts you are having, this place is looking whitish. Oh, where's my lesser? Okay, this area is looking white. This area is looking thicker or deeper in coloration. That is because of amplitude. Remember, I explained amplitude to you. So by looking at this seismic section in front of you, you are not seeing anything. You are not seeing the frequency. You are not seeing the wavelength. Typically, except more very experienced persons during processing, can I say this place is having high amplitude, high frequency noise and all that. But for an average person, when you look at your seismic data, you're not seeing anything frequency. To know the frequency, you need this software to maybe plot and give you the frequency reading within a particular section. But generally, what you'll be seeing is amplitude distribution. And this amplitude distribution is what you're interested in, is what you'll be interpreting. You can see the amplitude is high, but on this area, the amplitudes are low. They seems to be whitewashed. So why is the amplitude like that? The properties of the rock in terms of its velocity and density property, that's why you're having difference in amplitude display on your seismic section. And that is why anywhere you're having amplitude termination, you can identify such area and say, this is a structure, this is a fault, and all that. So for the reflection seismic method, we use it for detailed geologic survey. We use it to map layers of rock within the subsurface in terms of their thickness and the structures they contain. So the reflection seismic method gives you a kind of a true image of your subsurface. And for us in processing, we tend to say interpretable image of the subsurface, because that's the end thing. The subsurface image you get from your seismic method in reflection seismic must be interpretable and relatable to geology. Whatever you do, if it's not relatable to geology, you have failed on the project. Works effectively respective of situation of velocity reversals. For the refraction, I told you when the velocity of the rocks must increase with depth, okay? But for the reflection, there must not be any increase. And if this is the rocks, velocity 1, velocity 2, it doesn't matter who is bigger than who. Velocity 3 of the rock bodies, it doesn't matter. They can be increasing or decreasing. The side reflection has no business with whether this is increasing or the velocity is increasing or decreasing. It will always function properly. Okay. For your reflection, seismic data is always riddled with a lot of noise. So for acquisition within urbanized area is always difficult due to noise, and it requires so many shots and receivers during surveys. Okay. So the next thing I will be talking about, still on seismic, reflection seismic, is how does the reflection of the seismic data, seismic waves occur? During your reflection seismic survey, how does the reflections occur? How does reflections occur? So this is where we go back to our rock property in terms of velocity and density, okay? Your reflection will occur, as I mentioned earlier, at the rock boundaries, or at the boundary between one rock unit and the other, just as shown on this cartoon, there will be a reflection. But why? Why is there a reflection? If anybody will get curious, you can now ask, why would the rock even reflect? Remember, the rocks will reflect because they are sound waves. In elementary sound wave studies, we studied where you say sound waves, when they get to an interface, they will reflect. So your seismic wave is a sound wave. So it's going to reflect at this boundary. Why will it then reflect? It's going to reflect because of what? Acoustic impedance property contrast. Okay, there's a difference between the acoustic property of this rock unit. The first rock unit has its own velocity 1, V1, and its own density. Remember, we've talked about density. So this rock unit, whatever rock unit this part is, it has its own density and its own velocity. The second rock unit has its own density and the velocity, we call it V2 and density 2, okay? And then the third rock unit has its own velocity, okay? We'll call it V3 and density 3. And we've shown on the previous tables. So whatever the rock units are, let's say this is sandstone, this is shale, this is sandstone, this is shale, and this is limestone again. So their properties will differ in terms of their velocity and their density properties. So the product of the velocity of this rock unit 1 and its density, the product of its velocity and its density will give you what we call the acoustic impedance. So that acoustic impedance represented as the figure I. Acoustic impedance, some textbooks will say AI. It's not your AI that you're using to manipulate pictures and words and sounds and images on social media. But this time the AI is not artificial intelligence, acoustic impedance. Some textbooks will use the term AI, some will use the term I. So what it means is that the acoustic, the product of it was its velocity at its and its density. Okay. And then with the acoustic impedance contrast, property, there will be an acoustic impedance contrast at this boundary between this rock A and rock B. So at this boundary, which in geology we call the bedding plane, because the rock above has its own velocity and density property, which is it has its own acoustic impedance property, the rock below it will also have its own acoustic impedance property. So there will be a contrast between their two acoustic impedance properties. So that boundary, which is the bedding plane, okay, will be an acoustic impedance contrast boundary, and at that boundary, a reflection will occur. So that is primarily how the seismic wave reflects, and why we call it the reflection seismic. So when you now use this formula here, you get what we call the reflection coefficient. What it simply means is how much of the seismic wave will be reflected at this boundary. So as this seismic wave is traveling and getting here and is reflected, how much of it was reflected based on the reflection coefficients you calculate using the acoustic impedance boundary below minus the one above, divided by the one below plus the one above, you get a reflection coefficient, which tells you the approximate amount of seismic energy that was reflected at each boundary. Okay. This in turn will also point you to the amplitude of the energy that was reflected, and which you now visualize on your seismic data. So let's dive deeper. So for this image, you're having a seismic section and a cartoon rather, where a seismic wave is traveling from rock A, okay, rock A to rock B, okay. At the boundary between rock A and rock B, what happens? And this is rock C under. There's a reflection. So when that reflection takes place at this boundary, due to this one has its own velocity, as I've mentioned earlier. Change my pen color. This has its own velocity property, V1, and its density 1. And this has its own, which gives you what? The acoustic impedance, okay? I. So when you calculate the reflection at this point, the seismic wave will reflect. So the job of your receiver on the surface, which is your receiver here, is to measure the time that this seismic wave gets back to the surface. Okay? So when the seismic wave travels and reflects, it goes like this, travels to the boundary 1, and then go back to the surface 2. So this is why in seismic method, when you hear the two-way time, TWT, two-way time. You can jot that in your notes. Why? Because the seismic wave traveled from the source here down to this boundary and reflects back to the surface. So the traveling of the seismic wave will pass through parts, part 1 and part 2. Okay? So it's called the two-way time. And your seismograph on the surface, or your receiver, be it geophone or hydrophone, will record the time that the seismic wave got to this point. And so from this illustration, this boundary that caused the reflection, or the bedding plane, or the acoustic impedance contrast boundary that caused this reflection, will be recorded in your seismograph. And so this cartoon is showing a recording at about 0.7 seconds, for instance. 0.7 seconds. So if you can say 700 milliseconds, yeah, about the same thing. 700 milliseconds, ms. So that is that. So the seismic wave also travels through the it is continuous to be transmitted down through the second medium, or the second rock unit B. And so this rock unit have its own property, V2 and density 2. Please, for these cartoon illustrations, you can see that the rock units are uniform. And we are describing the travel path using a ray path, that's straight lines. So we are assuming that this is a homogeneous rock unit. So the velocity is uniform. The density is also uniform. So the rock unit is homogeneous. So or isotropic. I've explained that before. So we are assuming that the velocity is not changing in all directions. They are moving with the same velocity up and down. So the wave gets to the second acoustic impedance contrast boundary between rock unit B and C. It is reflected again. And this time, the reflection is traveling 1 to the boundary, 2 to the receiver, and it's occurring at 0.4 seconds. Sorry, 1.4 seconds rather. So this is also what you call your two-way time. Does that make sense? If you have any question at this point, I would like to entertain that before I continue. So that is the two-way time. So if I have to give you a simple exercise at this point, and I'll say at what let's say, for instance, we know that speed or velocity is equal to distance over time. And we have recorded time on the seismograph here to be 0.4 seconds. And we are assuming that the velocity that the seismic wave is using to travel through this rock unit is 2,000 meters per second. Can anybody tell me what will be the thickness of this rock in terms of distance? Because if you relate what I've just said to this simple equation, speed equals the distance over time, or velocity will equals the distance over time. So I'm assuming that the velocity of the travel of this seismic wave is 2,000 meters per second, for instance. And the seismograph has recorded that the wave came back to it at 0.7 seconds. What will be the depth of, or the thickness of this rock? A. I need someone to quickly calculate and tell me.
700 meters.
1,400 meters.
100?
700 meters.
Somebody
700
said
meters.
700 meters. So how did you get to 700 meters?
Yes,
Tell me.
I got 1,004. Is it?
It's 1,400 me I got to.
1,400 meters.
400 meters.
Okay. Who else got another? Someone else says 700 meters.
Yes, sir. 700 meters.
Okay. 700 meters. So for the person that said 1,400, can you tell me how you did it?
Since it's the velocity is 2,000.
Yeah.
If we make d the subject of the formula, it's going to be d equals v times t or vt.
Yeah.
So 24 times 0.7 is 14. I mean 2,000 times 0.7 is 14.
Oh, 14. Okay. Good. Okay. Just hold on to your information. 1,400 meters. So it's the person that says 700 meters. How did you get to 700 meters?
Okay, sir. Since it's a two-time travel, that means it has traveled twice.
Yeah.
The first one, that the total time taken was as captured by the seismograph is 0.7. That means it took 0.35 seconds to go to reach the boundary.
Okay. Did you get that for the person that said
another 0.35 seconds?
Exactly. That was what I wanted to get.
Sir?
So that means, yeah, you're correct. So this is the correct answer. This is the correct answer. 700 meters. This is wrong. Why I brought this out, so that you understand the concept of the two-way time. Two-way time. Okay? If I don't ask you the question, you will not understand the two-way time. So the seismic wave, the second speaker was right. The seismic wave traveled from the source to this boundary and back to the receiver on the surface in a total time of 0.7 seconds. So the time it took it to go from here to this boundary, which is from the top of this rock to the bottom of this rock, is 0.35 seconds. So your calculation should be 2,000 meters per second times 0.35, not 0.7. Does that make sense? 0.35. Or
yes,
you can say 1,400 meters divided by 2. So you can come back to 700 meters. So that is it. So that's this question. The aim of asking you this question is for you to understand the concept of the two-way time. So having this in mind, if I'm to say that the wave that propagated down to the contrast between layer B and layer C has a travel velocity of, let's say, 2,400 meters per second, what will now be the thickness of this rock. We are assuming everything at this point. Using this one. Using this arrival time.
Okay, 1680.
1680.
1680.
Okay. You applied your two-way time. I'm not calculating. I expect everybody else to be doing this calculation in the class.
Yes, I applied the two-way. I divided this 1.4 by 2. That's 0.7. 10 times 2, 4.
Okay.
That's 168.
Okay, that is correct.
1680, sir.
Okay, that is correct. So that is that. So you understand what it means by it. Wave makes a two-way time. It goes from your source to a boundary and then back to the receiver. So that is that. So you can, if you can arbitrarily on your own, you can then say, okay, because one, you don't know the depth in the subsurface where your rocks are occurring, but your seismograph are picking time values for you. Your receivers will be picking these informations in time. And that is what is recorded by your geophones or your hydrophones, time values of the subsurface rocks. It is these time values, which is the two-way time, that's the software that you're using for most times for us in processing, will use to get you back to the velocity of this rock. We'll explain that when we get back to processing. I will explain that when we get to the next class, or the next stage.
Can I
Pardon?
ask a question?
Yeah.
We're talking about the fact that this is homogeneous, and what if it is not homogeneous? Is it the same calculation when we are doing the two-way time?
Yes. It's the same calculation, but the heterogeneous situation becomes complex because within this rock, within this rock unit, for instance, this second unit that is a sandstone unit, the properties of the rock will be changing. Okay, so the densities are not going to be the same everywhere. Velocity will not be the same everywhere. So as the seismic wave is traveling and responding, remember, this is a simple cartoon. You have one receiver. During acquisition of seismic data, you have multiple receivers, more than 1,000 receivers, 2,000, 3,000, depending. So the different receivers are recording, even though the seismic wave is reflecting at this rock boundary. Let's assume this rock boundary is constant. But because the wave is traveling through this subsurface rock, at different depths, at different velocities, and their densities are varying. Their arrival time at different receivers will vary. I don't know if that this simple cartoon will not explain that properly. When we get to acquisition, I will explain that further. But just understand this on an isotropic situation, a simple situation. In nature, it's not this simple. In the subsurface, it's not that simple because in all directions, the waves are reflecting and coming back to the surface. Your receivers will be scattered everywhere in time on the surface, in space on the surface. So the different receivers will be picking different arrival times. Okay, so you will have variation in your acoustic impedance value. It will be varying. Okay, it will be varying. So the reflection time of arrival will vary because velocity will be changing because densities are also changing. So we will get further knowledge about that. Am I okay with that? Is there any other question? Okay. In the absence of any question, let's continue. So when this reflection occurs, at the boundaries between these rocks, when reflections occur, if the acoustic impedance contrast between the two different rocks is very small, okay, the reflection coefficients will be small. We've shown the calculation for reflection coefficients, where we say RC is equal to what? I above minus I below. Okay, that's I1 minus I2 all over what? I1 plus I2. Okay, so if the reflection coefficients you calculate, you get, if the contrast between these two rocks, okay, the contrast, the acoustic impedance contrast at this boundary is very small, very, very small. There will be a small acoustic impedance, a small reflection coefficient rather. So there will be a small, because there is a small acoustic impedance contrast, there will be a small reflection coefficient, and that will relate to small amplitude. So we will continue on that. Fejiro, are you still on the call? We are almost 2 hours into the class. I don't know.
Yes, sir, I am. Yes.
Do we
I
continue?
know I had to give you your own time because you found it interesting going through all the slides, and your students, no one has complained. So I don't know if they are tired already or if we should continue. But the maximum time for each lecture is usually 1:30, but it's depending on the mentor's schedule. But since you are fully available for us, maybe we can wrap it up by 4 or 4:30.
This is 4 o'clock. The remaining part of this lecture is not going to be finished in 30 minutes. That's why I have to call your attention. But I've laid the necessary foundation because I want you to have this understanding. The next lectures will be if we continue now, we'll be talking about these reflection coefficients and their effect on amplitude, which you see on your seismic data. I want to put fatigue into consideration.
Yeah, very important.
Talking for the past 2 hours and the students listening, but I think there should be a rest. So what we'll do is, and you see, I can't just dive into acquisition and interpretation without doing all this. And this is the foundation. A lot of persons who get into the industry and maybe they get into a company where they are doing interpretation, you see them on the workstation interpreting their faults and all that. But they don't have the fundamental knowledge of how they came to the data they are working on. Yes, you're applying your geology and geophysics to interpret the data. You need to understand the foundations, especially for anybody who is going to be a subsurface geophysicist, like your reservoir geophysicist, where you'll be looking at amplitude variations between the rocks and all that. You have to understand all these things because these are the things that causes those amplitude variations that you're using to make your decisions, okay? Like your amplitude maps that will tell you the reservoirs or that, whatever, and all that. So that is why I'm doing this. So we'll end the class now. This is 6 minutes to 4. We'll continue again. I'll need you guys to agree, okay? On the next time we'll meet, but because the next time we'll meet between now and Saturday, it will not have to be a Saturday, so that we'll clear out this introduction part, so that next Saturday we'll start the next topic. So I don't know, when would you guys be free? Within the week, anything in the afternoon sessions, maybe between 3 and 5, so that I can do that when I'm still in the office.
Oh, okay. So which means you need a session during the week next week before Saturday.
Between Monday and maybe between Monday and Thursday. So sorry, Thursdays are full for me, not Thursday. I have a lot of meetings on Thursdays. So between Monday and Wednesday, or maybe Friday, give me a time in the afternoon.
In the afternoon.
When is 12?
Is the evening, maybe towards the night, convenient for you?
Towards the night. For those that are
maybe
working
around
by 5,
7.
they are going on around 7.
7 or 8, any
Okay,
convenient
7 is not
time.
ideal for me. I'm in Port Harcourt, so when 7 or 8. Okay, let me see. Okay, you guys fix a date. I'll make it happen. It will have to be between 6 and 8, not 7.
6 and 8.
I can do that for you.
Okay. Maybe we can adjust to 6.
Date. Yeah, 6 is fine. So that we'll round up the class. You can go back and I believe I've made a few cents to you guys on so far. So Next time we'll finish that up.
Okay, please give me a minute. Is anybody
So you
joining
guys
this
tell me
session
when
with a
you
laptop?
take it.
Is anybody joining the session with a laptop? Sorry, Mr. Uche, I'm coming, please. Do we have any participant
It's only
joining
me
the
that's joining
session
with a
with a
laptop.
laptop? Oh, okay. I did not
I
join my
can't
laptop,
illustrate
so
all
I
these things
wanted
with a phone.
to take a screenshot of today's class.
For
Okay,
every other, oh, okay, screenshots.
Yeah, I wanted a laptop screenshot, but it will take time. If I'm to log in my laptop now, it might take me a longer time. Okay, no problem. It's fine. It's okay. Or should I just give me a minute? Let me see, because I need a picture for documentation.
Okay, what will happen is that I will save this. When I leave this presentation, I will not discard my write-ups. I will save them.
Oh, okay.
And send it to you personally at the end of the class.
Thank you so much.
I will save this. Also, when I'm sharing the slides by the end of our class, our next session, I will give you a version that has the scribbles on them and a version that is clean.
Okay, thank you so much, sir. So for the class, I will inform us on the maybe let me see. Please kindly drop your name for attendance now. You can drop your name now because we are wrapping up in the next 2 minutes. So please drop your name as fast as you can. Then for acknowledgement, we want to sincerely from the bottom of our hearts say thank you so much, Mr. Uche, because I went through all the session. I've been here with you too, and the session is very, very interactive. Students getting to know more from the beginning, because most often we do see the seismic processed data, very beautiful, but we don't know these are the things that have gone into bringing out a very fine chart for people to now interpret faults. So thank you so much for the mathematical basics that are needed. I know the geophysics, they enjoy more of this session because they are the one that will do all these calculations. Geologists are not too much of a kind. They